Newton's second law allows us to look a small time into the future and, given the F net, the system's mass, and final velocity, predict a system's position at a given time t. In this lab, I aim to analyze the motion of a mini basketball, our system, rolling across a table using Newton's second law to create a model of the ball's predicted position versus time. Using Tracker to analyze a video of the ball's motion, I generated the position versus time coordinates for the ball and created a model in Python to generate a set of predicted position versus time coordinates. Both datasets were then plotted and compared. Taking the F net to be 0 and the velocity to be constant, the result was a model that predicted the motion of the ball very well. The experimental setup took the positive y-axis to be pointing up, the positive x-axis to be pointing to the right, and the origin to be the center of the ball. As you can see in the video, the average point of mass for the basketball was tracked in Tracker as the ball rolled in the positive x direction. The points were compiled by Tracker to produce the following graph. The graph has a positive, seemingly constant slope, suggesting that the ball is moving at a constant velocity that was determined to be 0.7576 meters per second. From this data, I was able to generate a computer model of the ball's predicted motion during the time interval 0 to 0.933 seconds. The large blue ball in the model represents the basketball, and the green line the trail of the ball's motion. The graph seen being produced in the lower right will later be used to compare the experimental data with the model. Some of the most important aspects of the code are highlighted here. The ball's position vector was updated to the origin, and its velocity vector was updated to reflect the velocity previously calculated from the Tracker data. Additionally, the initial time was set to 0. The while loop utilizes the terminating condition of t final, here 0.933 seconds. The most important thing to notice here is that the vector representing F net has been set to 0. This is because, from the experimental graph, it was determined that the ball was traveling at a constant velocity. For this to be true, F net must be equal to 0. This is not to mean that there were no forces acting on the ball. After all, in this image from the first slide, several of the forces acting on the system were identified. An F net of 0 simply means that the sum of all the forces acting on the system was equal to 0. Finally, the ball's velocity and position were predicted iteratively at each delta t using Newton's second law. The velocity at each time t is calculated using a variation of v final equals v initial plus F net divided by m times delta t. Similarly, the position is calculated from r final equals r initial plus v average times delta t. Here we take v average to be the velocity calculated in the previous equation, which we can do this because of the small delta t. By plotting the x position versus time data from the experiment and the predicted x versus time data generated by the model, I was able to determine how well my model predicted the motion of the ball. As you can see here, the experimental data generated by Tracker very closely matches the model's predicted position versus time. The model slightly underpredicted the position of the ball towards the middle of the plot, which is likely due to a slight drift in the ball's path. However, overall, the model, which utilized Newton's second law and assumed a constant velocity and an F net of 0, did an excellent job at predicting the motion of the ball. A few follow-up questions arise from our results. Recall that originally the axes had been set so that the ball rolled along the x-axis in the positive direction. The question consequently arises as to whether flipping my axes would have affected my results. Had I changed my axes so that the ball rolled in the negative x direction, the conclusion of my experiment would not have changed. I could have chosen any labels and orientations for my axes without affecting the data in any way, as the axes are merely a way to measure and represent the vectors and motion associated with the ball. Visually, my model would have changed so that the ball rolled to the left instead of to the right, because when I inputted my initial velocity, it would have been in the negative direction. However, the magnitude would have remained the same. Additionally, one might ask whether we were able to deduce which and how many forces contributed to the F net of 0. As stated previously, F net tells us nothing about the individual forces acting on the system, only what their sum is. We are therefore unable to determine how many forces were acting on the ball, only that their sum was 0. Overall, it is clear that Newton's second law does an excellent job at predicting the future motion of a system moving at a constant velocity.